Hello. In this video, I'll present some open problems related to relaxed locally decodable codes. So before I start, I should say probably some of these problems are well known. Maybe others are very hard. Still, I think it's good to have all of them in one video. Okay, so below I'll present some problems related to relaxed locally decodable codes that I like. Before I present the problems, let me tell you what are relaxed locally decodable codes. So I think of a code as really an encoding procedure that takes k bits and outputs n bits. And we say that this code is relaxed locally decodable if it has a decoding procedure. And decoding procedure gets a code word W, so potentially it's a noisy code word, and it gets some coordinate I of the message. And it has the following guarantees. So if W is a code word, it's an encoding of some message M, then the decoding procedure must output the ith bit of M with probability 1. And this guarantee is robust. It's robust in the sense that even if a small number of bits of W are corrupted, namely it's close to encoding of some message M, then the decoding procedure still outputs either the ith bit of M, it either outputs MI, or if it sees a corruption, it's allowed to say, I see a corruption, so I'm not responding to this question. Okay, so with high probability, it must say either what's the ith bit of the message, or to say I don't know. And the important parameter here is the query complexity, which is denoted by Q. So this is the number of queries that decoding procedure makes to W. So the picture looks something like this. We have a local decoder. It gets a string W, and supposedly it's close to some message M, or some encoding of a message M. The decoding procedure also gets the index I of the message. It makes Q queries to W. And with high probability, it outputs either the ith bit of the message or it outputs I don't know. And if W is exactly a code word, then it's not allowed to output I don't know. It must output the ith bit of the message. And although here I make a distinction between coordinates of the message and coordinates of a code word, I really think of the encoding as being a systematic encoding. Namely, the first k bits of the code word really contain the message. So the local decoding procedure should correctly decode the first k bits of the code word. These k bits correspond really to the message. That's our definition of relaxed locally decodable codes. So the first open problem is the following. So we know that there exist RLDCs, relaxed locally decodable codes, where the query complexity is Q and the length N is equal to K to the power 1 plus 1 over Q. Okay, so it takes K bits of a message and it outputs N bits of the code word. And what's N? N is K to the power 1 plus 1 over Q. So as Q grows, the length becomes closer and closer to just being linear. But that's the dependence, 1 plus 1 over Q. Or I'm hiding constants there. On the other hand, recent work of Tom Gure and Oded Lahish showed that any such Q query RLDC must have length at least K to the power 1 plus 1 over Q squared. So the most obvious open problem is what's the optimal block length of a Q query RLDC? And if you ask me what's my guess, well, it's my video, so I may as well express opinions here. So the construction, to improve the construction, we would really need new ideas, I think. So it seems like K to the power 1 plus 1 over Q is the best we can get using these current constructions of this consistency test using random walks. On the other hand, for lower bound, there is one particular place in the proof that seems to be inefficient. This place uses some union bound, and if we could improve this union bound to some more sophisticated argument, then potentially it would improve the length. But again, that's only my opinion and I really don't know the answer. Right. So the first open problem is what's the optimal block length of a Q-query RLDC? That's problem one. Next, we may consider query complexity that's not constant, but maybe we can consider query complexity that's log n or polylog n. And we can ask, what's the smallest possible block length? For example, can we achieve block length that's quasi-linear in the length of the message? So for query complexity log n or polylog n, the only construction I'm aware of is taking just read-Muller code, so it's code of polynomials. And then the length would be almost linear, namely it's less than k to the 1.1, but it certainly doesn't achieve k times polylog k. So that's a nice open problem. And maybe I will be even more optimistic here, and I will ask, is it possible to obtain constant rate and query complexity is O of log n? So constant rate means that n is equal to 10 times k, and query complexity of decoding procedure is O of log n. So that's my second open problem. It would be also nice to think about the list decoding regime. So implicitly, so I didn't say it, but the assumption is that the given input word is close to some unique code word. Namely, if the distance of the code is delta, then the input W is at most delta over 2 close to some code word. So we're in this unique decoding regime. There is unique code word that's close to our input W. But we may consider also the analogous problem for the list decoding regime. Namely, we consider decoding radius almost up to delta. So there is a small number of code words there. Can we construct RLDC for this regime? I will not say much about this. So the next problem is relaxed locally correctable codes. So what are those? So we said that we think of our encoding as being systematic, namely the first k bits are the bits of the message and the rest are the encoding of the message. And in the RLCCs, so relaxed locally correctable codes, the decoding algorithm needs to decode not only the symbols of the message, but also the symbols of the encoding of the code word. So it needs to decode all bits of the code word. And here is an open problem. Can, in general, RLCCs achieve the same parameters as RLDCs? So is there a general procedure that takes a relaxed locally decodable code, which means that decoding procedure works only for the first k bits, and it converts it into an RLCC? Namely, it creates a decoding procedure also for other bits of the code word without hurting the length of the code word, without hurting the length of the code. And here's the fact, all constructions I am aware of, or all RLDC constructions I'm aware of are also RLCCs. So essentially, I don't know of any gap between the two. And it would be interesting to learn if there is actually a gap. All right, so next I'm going to relate RLDCs to locally decodable codes. So locally decodable codes are more basic objects, although they're also more complicated. So what's a locally decodable code? So a locally decodable code is exactly the same as RLDC. Well, RLDC is a relaxation of this. And the only difference is a decoding procedure. When it gets a word that's close to some when it gets a word W that's close to some encoding of message M, to encoding of some message M, it must output the ith bit of M with probability 2/3. Namely, it's not allowed to reject. Even if it sees that the word is corrupted, still it must output the correct bit of the message. And here is a very nice open problem to show a separation between LDCs and RLDCs. And recall that for locally decodable codes, best known constructions of such codes have only slightly sub-exponential length, while for LDCs we have almost linear length. So in terms of constructions, RLDCs are, well, seem to be a lot more efficient. So LDCs, the best constructions we know, require almost, well, maybe not exponential, but slightly sub-exponential length. And specifically, one possible approach to separating the two notions is to ask about their length. So is it true that any Q-query LDC is strictly longer than the best constructions for RLDCs? Specifically, the work of Katz and Trevisan, and there was a follow-up by Woodruff. So they showed that any Q-query LDC must have length at least k to the power 1 plus 1 over q. So there is some constant hiding there. And on the other hand, in the work with Vahid Asadi, we showed that there exists a relaxed locally decodable code of length k to the power 1 plus 1 over q. But the constants in the O and in the omega in the exponent are really don't show separation. So one of the constants is really larger than the other. So it's the right order of magnitude, but it still doesn't show separation. So in particular, improving the construction of RLDC to be just smaller by a constant that's well, to make the constant small enough will already show the separation. So I think that's an interesting open problem. Okay, so the problem is to show a separation between relaxed locally decodable codes and locally decodable codes. And the way to do it is to show a separation in terms of the length of the two objects. Here is another one. Another problem is can we understand lower bound? Maybe we can understand better lower bounds for locally decodable codes. So the construction of, so the lower bound of Katz-Trevisan and the Woodruff, they show certain lower bounds, but they seem to be quite weak. And the question, can we use these recent techniques of sunflowers that were used for relaxed locally decodable codes to show a stronger lower bounds for this notion of LDCs? And more generally, it would be interesting to apply these sunflower techniques that were used in this world of Gur and Lahish. Can we apply them to other problems? Can we apply them to other local algorithms? So it's sort of more general open problem that's that can have more applications than just to locally decodable codes, but to local algorithms in general. And maybe the last problem I will mention, this is sort of speculations, but anyway. So we said that the best constructions of locally decodable codes have only slightly sub-exponential length, so they have super polynomial length. The question, can we use RLDCs to construct better LDCs? So we know how to construct short RLDCs, and the difference is really, well, there's a significant difference. Yet, the question, can we transfer techniques from RLDCs to construct better LDCs? And for me, somehow the main technical difference is that a local decoder for LDC must be smooth. So what does it mean, smooth? Smooth means that each of its queries is almost uniform. So we start with, we want to decode a certain point in the message. And what we read is we read several bits from the code word, but each of these bits is uniformly distributed in the code word. This is not true for RLDCs, yet the techniques that are used to construct RLDCs, they have, some bits are truly uniform, some bits have, well, maybe are not perfectly uniform, but they have some entropy in them. So it is not unthinkable that the ideas for RLDCs can be transferred to construct better LDCs. But again, this slide says speculations. So I'm not sure if you believe me on this. Okay, so I think that's all I have to say. Thank you.